Hello, everyone. My name is Tim Hockin. I work at Google, and I've been working on the Kubernetes project since before it was open sourced.
Hi, I'm Bowei. I'm also work at Google, and I work on networking in particular on Kubernetes. And thanks to Valerie for some of the slide material. Today in our agenda, we will be going over two things. Really, this session is two presentations. First part will be an intro. This will be an overview of what the SIG does and some of the basics. The intro provides an overview of how networking works in Kubernetes, and we'll be going over infrastructure APIs and concepts. Basically, if you're new to Kubernetes or not familiar with the things that our SIGs deal with, this is for you. The second half of this presentation will be a deep dive. And really, we're going to look at sort of the new developments that are happening in the SIG. So this will be a deeper look at some of the newest work that the SIG has been doing. If you're comfortable with Kubernetes networking concepts and want to see what's next, this is for you. And especially if you want to influence the direction of the project, we highly recommend you listen to this presentation. Now, first, let's go over an intro to Kubernetes networking. So one of the natural questions for users of Kubernetes is how the project is organized and how it operates. So Kubernetes project is split into multiple special interest groups, which focus on various aspects of the system. And we break the project problem into aspects that are covered by these special interest groups. And SIG Network covers basically networking for the Kubernetes project. This is our charter. We're responsible for Kubernetes networking between various components, including pod networking within and between nodes, service abstractions, both for ingress, egress, and within the cluster, and then also network policies or security policies and access control. Below is a link to our Zoom meeting and our Slack. And don't worry, we will show this again at the end. Now, of the Kubernetes APIs that comprise the system, the networking APIs are as follows. We have services, endpoints, and endpoint slice, and these APIs cover service registration and discovery. We have an API called Ingress, which covers L7 HTTP routing. In sort of upcoming work, we have Gateway, which is a next generation HTTP routing and service ingress API. And finally, for security, we have NetworkPolicy, which is the application firewall. And SIG Network owns all of these resources. Now, to start off with, there's also the infrastructure of how these APIs are implemented. So at the lowest level, the low-level network drivers and how pod networking and connectivity is wired up is covered by what is known as the Container Network Interface, which is the kubelet implementation. Also included in Kubernetes networking is an implementation of the service API, and this is known as Kube-proxy. Also, there are many controllers that act on the API. For example, they implement endpoints and endpoint slice, the various service load balancer integrations, for example, the things that create load balancers or configure load balancers in response to services, and also aspects of network management such as IP address allocation or IPAM for pods. Finally, Kubernetes networking comes by default with a DNS system. So there is the Kube DNS implementation that handles name-based service discovery using standard DNS mechanisms as opposed to sort of via the Kubernetes API. So let's begin at the beginning. What is the Kubernetes networking model? So before we get too far into detail, it's worth revisiting briefly the basics. And the Kubernetes API networking model is that all pods can reach all other pods. Now this might sound simple, and the key here is that pods are not special from a networking standpoint. in many implementations, they will appear as yet another network endpoint. Think about the way your VMs and other network devices work. Now, while the concept is simple, there are actually many implementations. For example, there are flat, where the pods exist on the network directly. There are overlays, such as VXLAN, and there are routing-based configs, such as BGP. We won't be getting into the details of how to configure this aspect of networking today. It's more like an hour of its own, but we will provide references after the presentation. Now, Tim will talk about how services work in Kubernetes.
So I think it's worth digging into one of the more fundamental abstractions in Kubernetes, services. We have a fairly common situation. I have a client, and the client wants to talk to one of my servers. And I have a bunch of server replicas because availability, scalability. How does my client find and reach those servers? We've already established that pods can reach each other on IP addresses, but how does the client know how to find it and which one to use? Let's assume for a moment that it does some sort of name lookup and it picks one of the pods. But bad things happen. If I choose a server at random, what happens when that server goes down? The client has to reconnect to the server instance. And it has to pick a new server. Now, this sounds easy, but the truth is that most software out there does not handle this well, especially if the server's IP address is going to change. Pod IPs are ephemeral IPs, and clients can't rely on them. One of our main goals in Kubernetes was to work with open source software as it exists. So logically, we need something in between the client and the server. That logical something is a Kubernetes service. So to recap, pod IPs are ephemeral. The statement, I have a group of servers and I want my clients to find them, is a pretty typical thing. Services are how you expose a group of pods to your clients. Mostly that involves having a durable virtual IP, but you don't have to. That includes a virtual port and a TCP protocol or IP protocol. This is how we build service discovery. It has built-in load balancing, but it doesn't have to. You can opt out of that thing. We're not going to go into all the details of all the facets of service today. We just simply don't have time. So coming back to the problem statement, let's look at what really happens. The node runs a proxy which intercepts the traffic. Now, this API is pretty abstract, and the default implementation is in Kube-proxy, which isn't actually a proxy usually, but it does turn your node into a proxy. For example, we use IP tables or IPVS to make the node become your sidecar proxy. We'll get into that in a little bit more detail. So the client starts by doing a DNS query, and we'll talk more about DNS later too. DNS itself is a service in Kubernetes. That DNS service returns the virtual IP of the service that you're trying to resolve. The client now can connect to that virtual IP. The proxy will intercept the traffic and redirect it to the backend pod's IP address. Async to all of this, there are the controllers that are out there reading the services and the endpoints, compiling them down into usable data structures and publishing them for use by things like the proxy. So now what happens when a server goes down? The service here is hiding a lot of the details of what happens with a service. So when that server goes down, clients just need to reconnect to the same IP address, which honestly most clients can handle. Digging into services a little bit more, I'd like to show you YAML, because everybody loves YAML. What we have here is a service definition. This is what you would specify when you're writing a service. You can see that we have metadata. The name is my service and the namespace is default. We're going to use that as part of our service discovery system. the specification says which pods are mapped to this service. In this case, I'm taking all pods running that are labeled app, my app. And lastly, we define the ports. These are logical ports for your clients to use. That's the port. And then the target port is the actual port on the backend pod. The service allows you to remap these things, which makes a bunch of things easier. Once you submit that to the API server, it's going to fill in a bunch of other fields for you. It's going to default the type to a cluster IP, and it's going to allocate you a virtual IP address. It's also going to define the protocol by default, but you could specify that manually if you really wanted to. Now I'll hand it to Bowei to talk about the endpoints part of this.
A service is virtual, so how does the proxy know what pods to send traffic to? Like most everything in Kubernetes, it's yet another controller. Basically, the controller will convert the end pods using the label selector to a smaller set of endpoints. So how endpoints are represented is a list of IPs behind a service. Now, usually these are pods, but actually Endpoints API also gives you a way to put your own IPs and have custom controllers that do this. Now, remember that services had a port and a target port field. So in fact, the Kubernetes Kube-proxy mechanism can actually remap these ports given your configuration. And generally, these endpoints, most people use them, are managed by the system. So there's an endpoints controller that comes out of the box with Kubernetes. But as I said before, you can use them to generate custom endpoints as well. Now let's look in detail about how this works. So here we have a service, and its name is foo, and it has that app foo selector, as we said before. And along with the service, we have a bunch of pods who have app selectors. Now, not all of them are foo, only some of them are foo in this diagram. And the ones that are foo sort of comprise the service foo. Now, what happens with the endpoints controller is it will look at the selector in service, look at all the pods that have the appropriate labels, and create an endpoints object that comprises the endpoints of the pods that match the service. And this endpoints object is then something that will be fed into the rest of the system, for example, LoadBalancers, Kube-proxy, DNS, to tell the rest of the system that this service has these endpoints as part of the service. Now, as I mentioned before, there is DNS. So DNS is an integral part of service discovery. If you think of service discovery as being layered, you have the Kubernetes API, which is endpoints. Then you'll have traditional mechanisms to access the service, such as DNS, and then, of course, Kube-proxy. So DNS starts with a specification. There's a specification online of sort of the set of records that are generated in response to various Kubernetes APIs. And generally, there's a default implementation that runs as a pod in the cluster. But of course, this is not necessary. Any implementation that meets the specification will do just fine. And the DNS is exposed itself as a service VIP. But again, this is not required. Containers are configured by kubelet to use kubedns. And in fact, Kubernetes has an interesting concept that's sort of an extension on standard DNS behavior in that we use mechanisms to create aliases to make it easier for people to consume a service. Today, the default implementation in Kubernetes is core DNS. Now let's look at an example canonical name. So here we have my service, which is the name of your service, .default, which is the namespace your service lives in. And then there's this sort of a sigil, I guess, a token SVC that's just a constant that denotes it's a service. And then cluster.local is the cluster's DNS zone. Now, we note that because of the alias mechanism, you can actually say my service and expect to be scoped within your namespace, or my service.default to be scoped within a Kubernetes cluster. And these things are automatically handled for you through the kubelet DNS configuration injection. Now I'll hand it over to Tim to talk about how Kube-proxy works.
So we promised that we would tell you more about how the proxy system works. First, it's worth bearing in mind that Kube-proxy is the default implementation, but it is not the only implementation. It can be replaced. And in fact, we encourage people, if you have special use cases, to go ahead and replace it. It is an implementation of the APIs. So a Kube-proxy, by default, runs on every node in your cluster. It uses that node as a proxy for traffic from pods on that node. The mechanisms that we have built into it right now are IP tables, IPVS, user space. Windows has also a user space and an in-kernel options. In Linux, IP tables and IPVS are the more modern versions. The user space is less scalable and less behaviorally correct. In general, Kube-proxy is completely transparent to consumers. All those pods that are running on the same node don't know that Kube-proxy is there intercepting traffic. That's part of the API. So the way Kube-proxy works on the control path is it's going to watch all of the services and endpoints in the system, which we just looked at. It's going to apply some filters. For example, it's going to ignore some services that don't have virtual IP addresses. We call those headless. It's going to link those endpoints, the back ends, with the services, which are the front ends. And it's going to accumulate the changes to all of those. And it's going to then update rules on the node to represent those changes. For example, in IP tables, it will capture traffic destined for the virtual IP and port, and it will redirect it into the data path to handle the data path. On the data path, it's going to, like I said, recognize the destination IP and port. It's going to choose a backend pod, generally. It's going to consider things like client affinity. Have there been other sessions from this client to this virtual IP if the service has requested those? And then it's going to rewrite those packets to a new destination. That's destination NAT. On response, it's going to apply the opposite of that and un-DNAT it and return it back to the original client. Again, the clients are unaware of what's happening here. This is all happening on the node as a service to the pods on the node. So we hear this a lot. Why don't we just use DNS round robining for load balancing? Why is this so complicated? One of the fundamental things we learned about Kubernetes very early on is that most DNS clients are broken and they don't handle things like DNS records changing very well. Many applications never re-resolve the names that they've looked up. This abstraction provides a stable IP address so that clients can work as they existed before Kubernetes in a world where durable IP addresses were more prevalent. For those clients that are enlightened and can actually handle this properly, can you opt out of this stuff? Of course you can. This is Kubernetes. You have a million options. There are things like headless services, which allow you to do DNS round robining without a virtual IP address and without any NAT translations. Alongside services is the load balancer system. Services are how you expose load balancers in Kubernetes. We have different load balancer implementations, and they work in very different ways across cloud providers and across mechanisms with your networking. It's a little too broad for us to go into this talk, but there are other talks online that you can watch that will go into this in great detail. Most cloud providers have implementations of load balancers for services in Kubernetes. Now I'll hand it to Bowei to talk up one more level.
Thanks, Tim. So we saw that services describe L4 protocol-based services, but what about L7? And this is where the Ingress resource comes in. So what an Ingress resource does is it's an API to describe an HTTP proxy and routing rules. So this is a very simple API to match host names and URL paths. It might be too simple, so we'll see more on this later in the deep dive. And what it does is it targets a service for each HTTP URL path rule. Now, Kubernetes defines this API, but the implementations are all third-party and integrates with most clouds and popular software LBs. In fact, I think there are quite a few Ingress implementations. So let's go over sort of what the shape of this API looks like. So here we have a Ingress configuration along with the services and pods. And you'll see at the top, there's an Ingress with a host name and a bunch of paths. And each path corresponds to a rule that then maps to a specific service. So you can imagine there's a path for /store, and that will be your store service. And there's a path for /search, and that will go to your search service. And then the services are used as a way to select which server pods are implementing that service. For example, in this case, the foo service will be implemented by backends with the label app foo, and the same thing with the bar service. Now, a couple of questions come up, which is one, how is this different from service type load balancer? So I think the difference is that service type load balancer is constrained at the L4. It doesn't talk about anything higher in terms of load balancing. And Ingress provides a way to describe these things. And the other thing to note is that when you go to L7, it is very common that you will be composing services, multiple L4 services together to create a single L7 service. Second question is, why isn't there a controller in the box? So there were actually many, if you think about the overall L7 proxy landscape, it is a pretty mature landscape. There are many implementations, many different proxies, and we didn't want to pick a winner among the software LBs. However, it is an interesting point to have a system that has batteries included. Next, Tim will talk about network policy.
So you can't really have a network without some way of describing what's allowed and disallowed on the network. Network policy is the Kubernetes API that describes the graph of your application. It allows your app developers to express what do you expect to be happening here and disallow everything that isn't expected. So for example, you could have all your front ends which talk to your back ends and your back ends which talk to your databases, but you'd never want your front ends to talk directly to your database. That would either be a bug or something even worse. Like Ingress, network policy implementations are all third party. It's very likely that the implementations of network policy are very coupled to the way your network is configured. And so it didn't really make sense to have an in-the-box version of this when we don't have an in-the-box version of pod networking. Network policy is a very simple API. It's very focused on application owners rather than network administrators. And we may yet need another API at a higher level for network administrators, but network policy is really supposed to be part of your application's description. So you can see here the example that we mentioned. All the front ends can talk to all the back ends, and all the back ends can talk to the databases. But you would never want your front ends to talk to your databases, or for your front ends to talk to other front ends. That might represent that you've been compromised and someone was trying to do a lateral attack. Network policy lets you describe the green lines, and everything that's not green is automatically blocked. So now I'm going to hand it to Bowei to dig into the details of some of the ongoing work in the SIG.
So hopefully that gives you sort of a coverage of at least the table of contents for Kubernetes networking. We know that was a lot of material, and we'll be happy to answer lots of questions at the end of this. So as part of the deep dive, we're going to look at a closer look at the work that's happening in SIG network. So some of this is at GA, and others are in alpha and beta stages. And I'd like to repeat that if you're looking to influence the direction of Kubernetes networking, we really value feedback and participation from the community here. And the ongoing work in the SIG that we're going to highlight for the deep dive are Endpoint Slice, which is work in scalability and extensibility, NodeLocal DNS, which makes DNS more scalable, all the factoring around services, sort of thinking about where to go next with services, and finally support for IPv4 and v6 dual stack. So NodeLocal DNS was a project that was initiated because we knew from copious feedback and issues on GitHub with many, many comments on them, that the Kubernetes DNS resource cost is quite high, right? So this is partially due to the expansion due to name aliases. So it turns out that using an alias mechanism results in potentially, with IPv6 enabled, a 10x query explosion. But it also has to do with the fact that as Kubernetes users, we have higher application density. So we have lots of microservices. So we see lots more DNS clients. We see that lots of modern application libraries and infrastructure, such as Node.js, are quite DNS heavy in their default configuration. And finally, that the Kube-proxy, at least with IP tables implementation, the use of contract and various connection tracking mechanisms in the kernel also have a bad interaction with UDP, which is the transport used by DNS protocol. So as DNS is the canonical example of achieving global scalability through caching, the answer is simple: run a cache on every node. However, we have to be very careful because, as it turns out, if you run something per node, actually the overhead can dominate in large clusters. So we have to be very careful, and in fact, the NodeLocal DNS is an extremely slimmed down, very small local cache that's based on core DNS, but basically without many of the plugins compiled in. As a system critical component, which is in a daemon set, we also have to be quite careful about high availability during upgrades and failures. And this was one of the gating criteria for the GA of NodeLocal DNS. So let's go into how NodeLocal DNS looks on your system. So here we have sort of how DNS works without NodeLocal DNS. So you see in green, you have a set of pods, and Kubelet has configured for your pod the upstream DNS resolver, which is, in this case, 10.0.0.10. And KubeDNS will use the standard Kube-proxy service mechanism that we described before to reach the backends of the DNS system. Now, when you enable NodeLocal DNS, what you'll see is that it inserts itself as a daemon set on your node. As part of this, it creates a dummy interface. This is in orange here, with binding to 2 IP addresses. And along with it, it inserts a bunch of node track entries for those service VIPs on the local node. What this does is, with node track, you avoid the usage of contract entries for the UDP packets, so it will skip Kube-proxy. The secondary effect of the interface and the binding of the VIP is that actually this allows NodeLocal DNS to capture the VIP traffic and sort of live alongside Kube-proxy. You'll notice that we still have to go upstream to KubeDNS. So how do we do that? We actually create another service that tells the NodeLocal DNS about the upstream, which is this KubeDNS upstream here. This is the 10.0, and then the cluster VIP will be allocated from your cluster VIP range. Now, you'll notice what a very interesting thing here is that these two mechanisms live side by side. And in fact, for HA and upgrades, for example, if the NodeLocal DNS goes down, it has a watcher process that will remove the node track. And once the node track entries are removed, actually the standard Kube-proxy service mechanism will happen. Your pod will talk to KubeDNS and seamlessly fail over to the old mechanism. So this allows us to not only manage upgrades, but also situations where NodeLocal DNS has failed for some reason, and we are able to at least default you back to the KubeDNS infrastructure. So one final note on DNS is we can do better. So even though NodeLocal DNS handles some of the load issues, it is still yet another agent doing DNS in your cluster to handle some of the query expansion for the aliases. So there is a proposal as a KEP to push alias expansion into the server, the DNS server, as an API for Kubernetes. And what this will do is to make some of the mechanisms and plugins that lots of people use, such as the core DNS autopath plugin, actually pull that into a standard Kubernetes API. Finally, one other topic that sort of is interesting is how do we refactor the DNS naming scheme altogether? So some of the search expansions and aliases may not be necessary, but also what kind of improvements can we make on the schema. The next topic for our deep dive is also partially scalability and partially extensibility. So as we talked about before, there is an Endpoints API that serves as a service discovery mechanism for Kubernetes at the Kubernetes API level. Now, in larger clusters, think 15K nodes, for instance, and very large services will lead to an API scalability issue. So if you think about it, an endpoints object is a single object, and let's say you have 1,000 endpoints. All 1,000 endpoints will have to go into that single object. If you keep expanding services and the number of backends in a service, eventually this will exceed the size of a single object in etcd. Now, of course, you can reconfigure etcd to support larger objects, but there is a limit to that. You can conceivably double the size of the object, maybe triple it, but at some point you're going to have to live with the limits of etcd. Also, a huge issue is the number of watchers for endpoint objects. So as you recall, Kube-proxy watches the endpoints objects in the cluster, and there is a copy of Kube-proxy running on every single node. In addition, other controllers may be watching endpoints as well. And what this does is it creates a large amount of data that needs to be sent to the watchers. So in this example below, and we have 5,000 nodes. Let's say the size of each endpoint object is 1 megabyte. And if you have an update to the endpoints object, it will actually send 5 gigabytes of data. Now, this is basically a DVD. And then if you do a rolling update where you are slowly changing the endpoints one by one, and you imagine these updates propagating through the system, by the end of your rolling updates, this will be 25 terabytes, which is a lot of data. So the idea of endpoint slice is that instead of a single endpoints object, we in fact have slices of endpoints and then sort of create a relationship between the endpoint slices and the services in a different mechanism. Here we have a diagram of what the endpoints objects update looks like for an endpoints object. So here we have at the top the resource living in the API server. So there's like a single resource, and we perform a single update, which is the yellow highlighted endpoint here. But for each Kube-proxy in the cluster, we actually end up having to send the entire endpoints object. Even though that little piece changed, we have to send the entire thing. With endpoint slices, what happens is that that service is in fact instead represented by a set of endpoint slices. So there are actually many endpoint slices for a given service. And if you see, and they are each of a maximal size. By default, they will have 100 endpoints each. And a single update to an endpoint actually only needs to send the slice. So you'll see here that highlighted in red, that endpoint slice object, abbreviated EPS, will be sent to these Kube-proxies, but the ones that did not change will not be sent. So to implement endpoint slices, there are a couple of controllers that are needed. There's the endpoint slices controller, which basically creates slices from the service selector. And you'll notice that these are linked to the service via labeling and selection. It's a standard Kubernetes mechanisms. Also, we notice that there is another interface that people use for the Endpoints API, which is to custom populate Endpoints APIs that are outside of the standard Endpoints controller. And this is handled by the Endpoint Slice Mirroring controller, which mirrors endpoints from endpoint resources that are sort of populated outside of the controller into slices as well. Finally, the Endpoints Slice API, we know that lots of people will want to extend service discovery. So it is in fact designed to be a generic service discovery mechanism, and other users can set this annotation to specify who is managing the endpoint slices. So sort of more detail on how endpoint slices work. So it turns out the update algorithm is actually an interesting optimization problem. So at the same time, you want to keep the number of slices low, because you don't want to create too many resources and start running into etcd write issues in terms of number of resources you need to write to the database, while minimizing the number of changes to the slices per update, because we don't remember every single change in every single resource needs to be sent out to a watcher, and of course keep the amount of data sent low. So these are kind of somewhat intersecting, and you can imagine that to keep the number of slices low, you might need to make more changes to slices and so forth. The current algorithm that we have settled on is the following. The endpoint slice controller will go over all of the endpoints, first remove stale endpoints in all the existing slices, and then fill in new endpoints into the free space, and then finally, if you have no space left over, to create new slices. Now, you'll notice that this has no active rebalancing, and the claim is that we can do active rebalancing, but it will be too much churn. Of course, this is an open area, and since endpoint slice is in beta and going GA soon, we would love to see how people's actual experiences with this algorithm shake out. And just to go into kind of the timelines, because this is a core API, its rollout is going to take a couple of releases. So in 1.17, the endpoint slice controller and API was available. In 1.18, we made the controller enabled so that the resources will be created, but Kube-proxy will not be defaulted in. And then 1.19, we expect endpoint slice controller, endpoint slice mirror, Windows, and Kube-proxy enabled. And finally, in 1.20, it will be GA. The reason that this has to be staged is to basically take care of the fact that you don't want a race condition when you're upgrading between Kube-proxy consuming endpoint slices and the endpoint slices actually existing in the cluster. Next, I'll hand it to Tim to talk about services across clusters.
Thanks, Bowei. As Kubernetes users become more prevalent in more market segments and their installations get bigger, their needs get bigger, it's becoming very common for users to have more than one cluster. And we have a lot of reasons why users have more than one clusters. Some are HA, some are blast radius, geography, legal restrictions, dev, test, prod environments. I can probably give you 25 reasons why people have multiple clusters. The problem here is that services have always been a cluster-centric abstraction. We're now starting to work through how do we export and extend services across clusters. And this is a collaboration with the SIG multi-cluster. This comes up as one of the most common pain points that we hear from users. For example, let's look at this situation. I have two clusters, A and B, and I have my front-end service in cluster A and my back-end service in cluster B. How do I get my front ends to be able to reach my back ends? This seems like it should be easy. There are ways to do this, generally involving load balancers and translating from one IP space to another or rewriting packets, but I think we can do better than that. So one of the things that we're starting to look at is what if we could expose services between these clusters? So for example, given the service on the left, the back-end service, what if I had something like the right that simply declares that this service is exported, right? But what does it mean? Exported to what? So first, let's assert that a group exists. I'm not defining the group. I'm just saying that it exists. This leaves a lot of room for interesting implementations, for vendors, and for people to try different things with their grouping mechanisms. So let's just assume that it exists. And within that group, these clusters are related. Within the group, we're going to assert that namespaces mean the same thing. And that's a pretty vague term. What it means is there's a single owner for a given namespace, regardless of which cluster they're talking about. So what that really means is this: that service logically exists across both namespaces. The namespace exists across both clusters, and even if it doesn't physically exist in the other cluster. That means that we can start to build controllers that operate across those clusters. In this case, we wrote this service export controller, which triggers that we go out to each other cluster and republish that service for them to find it across the different clusters. So in this case, it will create a service import, which is the opposite of a service export. And we'll get to more of that in a second. And it will also create endpoint slices in your local cluster, which represent all of the backends for this service across all of the clusters. We'll get to that in a second too. In this case, we just have the one cluster that's exporting the backend service. Now, clients in my front-end service can access my backend service the same way that they would access any other service that was in their cluster, except it's not just in their cluster, it's in a different cluster. So we looked at DNS before, so we'll look at DNS again here. Similar to the main DNS, we have backend service, which is the name of my service. We have backend, which is the name of my namespace. And we have a new suffix. The suffix here is to be decided on the name, but right now we're running with supercluster. Will give you a different zone. And by simply changing the zone that you use, and from cluster.local to supercluster.local, you have now enabled multi-cluster services, assuming that you have this controller that is operating across your group. To make it even more fun, that backend service might exist in both clusters. In this case, accessing the supercluster service will use backends in either cluster. You can see there's a lot of lines in this drawing here, but both clusters will have endpoints and endpoint slices that represent the union of all of the backends across both clusters. Now, to be fair, this is mostly kepware right now. There's some proof of concepts that exist. We're still hammering out a lot of details, things like API and names. We have a poll running on what the proper suffix should be. We're still working out some of the semantics, for example, conflict resolution and propagation time and scalability. We're still looking at things like cross-cluster network policy, which doesn't quite exist yet. But we're excited about this work that's coming. Again, this is a collaboration with SIG Multicluster. So I also want to talk about some of the exciting work that's being worked on right now. IPv4 and IPv6 dual stack. The reality of the world is that some users need both IPv4 and IPv6 at the same time. Kubernetes has gotten this far by assuming that there's a single IP address for pods. We've also gotten this far by assuming there's a single IP address for a service. If we're going to exist in a dual stack world, we have to fix this. This is a small change to the API, but it's actually very profound and the impact of it is pretty large. Now, some of you may be asking, wait, wasn't this done already? Didn't you talk about this before? Yes, we did. We got this to alpha and we found a bunch of significant problems with it. So we're doing a major reboot of the API. So I thought it was worthwhile to throw out the new API here. So starting with a plain old pod, we had this. Now we're going to have this. So we're going to take the pod IP field and we're going to pluralize it. And we've worked out a protocol for what pluralization means within the API. And it involves synchronizing the legacy singular variable into the plural field. It's always going to be the 0th element of the plural field. So you can see here 1, 2, 3, 4 is the same in both cases. And now we have a place where we can add our secondary IP address. Similar to that, you can see we have nodes. Node has a single pod CIDR for a single IP family. That now becomes a plural in the same way that pod IPs became a plural. Again, you see the 0th element maps to each other, and now we can add the IPv6 address alongside it. Now it gets a little bit more fun. I've got a service and I've typed cluster IP, and I've got a single cluster IP. This is going to become this, which is a little bit more involved than what we saw before. You can see the same pattern of synchronization between cluster IP and cluster IPs, and you can see the new field, the IPv6 field, being added. But there's also a couple of extra fields. These fields are here to tell the service subsystem, what did you want? you can see that there's a policy which lets the user express various things. I'll get to that in a second. And an IP families list. This is what has been allocated to this service and what consumers who are using this service, such as Kube-proxy, can use to route traffic into this service. There was a bunch of different requirements here. We needed users to be able to express things like, I need single stack, and not just I need single stack, but I need single stack and I need it to be specifically IPv6. It was also important that people be able to express, I need dual stack, and if I don't have it, I want you to fail. And in between those two, people who would say, I'd like dual stack if it's available, but if it's not available, that's okay. And so this API allows users to express that. But if a user doesn't express anything, if you take a service that exists in Kubernetes today and bring it into this dual stack enabled cluster, you will get a single stack service. This works for VIP services. It works for headless services. It works for node ports, and it works for load balancers, assuming that your cloud provider supports load balancers on different protocols. That's a cloud provider decision that they're going to have to make. So this work was alpha, and it is alpha in Kubernetes 1.18 and 1.19. We're shooting for a second alpha in 1.20. This is a breaking change from the API point of view. Because we're still in alpha, we can technically do that. It's unfortunate for people who have started using it, and to all those people, I apologize. Hopefully we get it right this time. I'd like to hand it back to Bowei to talk about what else is upcoming.
Thanks, Tim. So as part of thinking about services, we titled this Services V+1, is we are looking at sort of what the evolution of services is. And if you think about it, currently Kubernetes service is a number of things. One is it's a method of exposure. So on the side, you have here the hierarchy of different service types, such as headless, cluster IP, node port, and load balancer. And in fact, they imply, for example, a load balancer implies a node port, implies a cluster IP, and so forth. The second thing that a service does is sort of talk about groupings of pods into a workload, which is a service, e.g. the selector. And finally, the service resource contains things which is attributes about the service, about various policies, such as external traffic policy, session affinity, and so forth. Now, what we're finding is that evolving and extending this resource has become harder and harder because all of these fields, they sort of serve different purposes, but they, as part of the same API, they will interact in strange ways. At the same time, there's been an evolution, a desire to evolve the L7 Ingress API. As I said before, it was fairly bare bones and simplistic. And a lot of the proxy vendors today can support much more expressibility. And we also want to incorporate, as part of this division of responsibility and resources, that allows for modeling of different roles. So it's both, what do we do about extending service further, and also how do we describe some of these things that we know exist and can be done? So the idea of services V+1, which is also known as the Gateway API, is to sort of decouple these things along a role and concept axis. So we have a bunch of roles, which is, and apparently the emojis did not translate well into PowerPoint. So there is supposed to be some, you see the female sign is actually supposed to be an emoji. So there are a couple of roles that we're looking at in terms of modeling these resources. There's an infrastructure provider, which is sort of the set of people that have set up your cloud environment, your cloud platform, have created your cluster. There's a cluster operator who are sort of the super user of an individual cluster, or network operator who control, say, who can have access to internet access and egress proxies and so forth. And then finally, there's the application developer. So what we want to do with the services API is to basically allow a user to express these roles and sort of grant different permissions based on these different roles. The second thing that we wanted to do in sort of service refactoring is to separate these concepts into different resources so that the evolution of each of the resources can be much easier to deal with. So the three concepts I said before are grouping and selection. So this is sort of what workloads comprise a service. The second piece is how routing and protocol-specific attributes will work. So for L7 HTTP, this will be, for example, that a given host name and a given path will go to a particular service. And then finally, the last part is how the service will be exposed and how it will be accessed. So we'll kind of go over a high level of what this looks like in the API proposal. So at the top, we have, and you'll see on the right, we have the various resources that are being developed. So at the top, we have gateway class. So a gateway class is a resource intended for the infrastructure provider. And what a gateway class describes is it defines a kind of service access to a cluster. For example, example gateway classes would be, for example, an internal proxy, like a proxy, like say Nginx Ingress that runs on the cluster, or an internet LB, for example, a kind of proxy that runs in the cloud provider infrastructure. So similar to storage class, this abstracts the implementation of the mechanism. For example, an internal proxy may use a specific version or deployment of a L7 proxy from the consumer. So from the consumer standpoint, they would just say, I want to have an internal proxy, or I want to have an internet LB. And then the cluster operator, the infrastructure provider, will create this class to sort of say, hey, you wanted an internet LB, this is how we're going to actually do it. And below, you can see an example of the configuration for a gateway class. You'll see that it has a controller. So for example, if Acme.io was a proxy implementation, and this would be the controller for Acme.io, and a way to pass controller-specific parameters to it. But from the user standpoint, for example, people who create gateways and routes and so forth, they will only know that this gateway class corresponds to a in-cluster gateway, which is sort of the name here. They wouldn't have to know, for example, that in actuality, that in-cluster gateway is implemented using an Acme.io gateway controller. Uh-oh. Next, we have the gateway resource. So the gateway resource is what we would typically think of controlled by the role of a cluster operator or network operator. And this governs how the service is accessed by the user, e.g. what port it's on, what protocol it's on, what addresses it uses. This is a keystone resource. What I mean by that is this will be one-to-one with the lifecycle of some infrastructure action. So it'll be a configuration of infrastructure will be triggered by the association of a valid gateway with a class and a route. And this could have many implementations in terms of deployment. It could spawn a software LB. It could add a configuration stanza to an LB. It could program the SDN and so forth. But basically, the gateway sort of hooks all of the resources together and provides that lifecycle relationship. Now, one thing to note is that a gateway may be underspecified, quote unquote. For example, there may be many defaults that are sort of provided by a gateway class. So the user needs to concern themselves with aspects of the gateway that they care about, and the gateway class will provide most of the other things. So if we take a look at an example gateway, we have a gateway that has a class cluster gateway, which we mentioned before. And we say that the user of this gateway says, I need a gateway that has port 80, and then I'm going to associate a couple of L7 routes with this, but no more. And the gateway, cluster gateway, if it is able to do so, will be able to populate the rest of the gateway, such as the address and where it's located. Finally, we get to the route resources. So route resources are a protocol-specific description of how to compose services together into a overall L7 description. Now, we would typically expect the application developer to be writing routes. And this will be pretty standard in terms of they will be, for example, talking about composition, such as search going to a search service and a store going to a store service. And here you see a little asterisk there is that actually this is a family of resources. So it's a family of resources grouped by protocol and use case to solve the issue of, for example, in the API defining a single closed union type basically a single type that has all the possible types enclosed in it. That probably will make it very hard to evolve it quickly. For example, the single API type needs to talk about TCP, needs to talk about SNI, needs to talk about HTTP, and so forth. It also precludes extensibility by, for example, an infrastructure provider providing their own routing types for, say, special protocol that wouldn't make sense to put into the standard Common Core. Now, what about service? So service is at the bottom. So we see that service probably should retain its place as a grouping and selection mechanism. And of course, since the V1 functionality is GA, that will still work. But hopefully, with this new decomposition of the resources, we won't have to add significantly to the existing surface area. And that'll really help us evolve things as we go forward. So here we have an example of sort of how all these things are hooked up. We have a gateway class that is referenced by a gateway, and the gateway references other routes in green. And then finally, the routes route each of the interesting paths and protocol-specific matches to their respective services. So we're still working on the V1 Alpha 1, but this is a cut list of the things that we really want to get done. We want to demonstrate basic applications and the data types, which is the resources. We want to show that gateway class can be used for interoperation between controllers. So we want to have 2 controllers or N controllers and then sort of switch the classes between them and see that working. Basic support for HTTP and TCP as 2 examples, one at L4, one at L7. Of course, HTTPS. And then finally, implementability. We want to have implementations demonstrate a wide range of how it's being done. So there's the merging style, which is multiple gateways hosted in a single proxy infrastructure. And then there's also the cloud provisioning style in which gateways are mapped to the externally managed resources. Finally, I'll hand it over to Tim to wrap it all up.
Whew. Thanks, Bowei. So we're getting close to an hour of talking, and I know that there's a ton of details that we've thrown at everybody. I want to say this is just some of what we're up to. The SIG at large is dozens of people who are working and sending ideas and new features and writing KEPs. It's amazing and overwhelming how much has been happening in SIG Network this year. So I want to send a special thanks to everybody who's part of SIG Network for doing all of this amazing work. We have an issue tracker. Of course we do. You can go to issues.kates.io and you can file bugs if you find them. You can go look for cleanup ideas if you want to contribute, or you can file feature requests or come and help us with things like triage. This is something we do on a bi-weekly basis with our SIG calls, which again, we'll post the Zoom link in just a minute. Come and help. The issues are a great place for people to get started and get involved. Come and look for the problems you've had or help other users with the problems that they're having. We also have a repository for our enhancements, our KEPs, our Kubernetes enhancement proposals. These are user-visible changes, usually features, but sometimes they can also be non-functional changes like scalability, but mostly they're user-visible things. We welcome anybody who's watching to participate in our enhancement conversations and the planning. We always welcome more eyeballs, help us find new problems, ask great questions, or come and submit an enhancement proposal of your own. If you've got a problem with Kubernetes, we want to hear about it. Lastly, to get involved with our SIG, you can find all of our information at our SIG Network community repo. We do meet every other Thursday at 2100 UTC. We have a Slack channel, SIG Network, on the slack.kates.io Slack server, and we have a mailing list. So there's got to be something in here that works for you to get a hold of us and come have a conversation. With that, I want to say thank you to everybody who came today, and thanks to Bowei for all of her hard work on this. Hi, everybody. I guess we're live now. So we have a bunch of questions. Boy, I don't know if you're on mute, I think.
Yep, I just
we have a bunch of
off.
questions. There we go. We've done some rough categorization of them while people were asking them. So I'll just go through and I'll read the questions out, and we'll answer them. And feel free to submit new questions, and there are people prioritizing those too. We'll try to get to as many as we can, and afterwards we'll jump to the Slack channel. Question, our team is using GKE and we had multiple problems running out of contract. We had to deploy a daemon set to customize it for our needs, and there were some follow-up questions that the usual answer of NodeLocal DNS isn't solving the problem. So we've seen it with a small number of users. Not a large number of people actually run out of the contract records. We set up a lot of records. There isn't a general answer. What you're doing with the daemon set is a good way of customizing nodes. I'd love to talk to you and understand exactly what sort of records are being stuck around in your system. UDP is generally a culprit here, but if it's not UDP, I'd love to understand what exactly is happening in your system so we can see if there's a more general way of solving the problem.
Yeah, I think we've found that mostly the contract is actually pretty high, so there must be something special that your workload is hitting.
Yeah, unfortunately, it's hard to do contract very dynamically. The kernel does a lot of work when you change the size of the contract tables. Next question. When I deploy a load balancer IP, if I don't specify an external IP, will I still be able to access it outside of the cluster? Load balancer services are, quote, external to the cluster. So the idea is, yes, you'd be able to access that load balancer IP from outside the cluster. What exactly that means really depends on the implementation. So for example, on Google Cloud, there are two different kinds of load balancers that you can choose. One which is external to the cluster but internal to your private network, and the other which is on the internet.
Do you want me to read the next question, Tim?
I'm just seeing if you have anything to add. Next question. If my service has 3 pods and Kube-proxy runs in IP tables mode, i.e. 33% randomness, how does it cope if one pod crashes? How long is the delay before it figures out one service pod is down? So the delay is generally as long as you've set your readiness probe on your pod. So if your pod is down but alive, like it's running but it's not serving for some reason, your readiness probe will trigger the update to the pod. Generally, readiness probes are on the order of single-digit to 2-digit seconds. Most people configure them that way. So it will be a few seconds before it's removed from the service. If you don't have a readiness probe, A, you should have one, and B, we won't know. If your pod actually crashes, we'll know pretty quickly because it will no longer be something that the service controller is selecting. So that is the quickest way of getting it removed from the set.
Yeah, and then I think there's also a work on getting SLI, SLOs for how long it takes to propagate. And if you're curious about details, you can ping me on Slack.
Yeah.
So this is in addition to your readiness probe.
Right. Next question was regarding Ingress. Why not include a controller now that we know better? Bowei, you want to handle that? Why not put a controller in the box?
Yeah, it's an interesting question. I think it still returns back to the fact that there are many controllers and there are many that are quite popular. It's sort of tough to sort of pick a single one. I know that I think the Ingress Nginx is quite popular, but there's quite a few, and including those by vendors and those in OSS.
Yeah,
so it's going to be very hard to choose.
My fear with putting one in the box now is most people have already compensated for this, either in the distributions or in their own clusters. Putting one in the box seems like a recipe for breaking people, and it may be that it's just too far gone to try to fix that.
And I think the next question is the same.
Oh yeah, I just moved that one out. For years, people talked about IPv6 as a replacement for IPv4. Yes, literally decades. Why Kubernetes pods are still using v4 by default and not v6. v4 by default because it's ubiquitous. We know it works everywhere. For example, all the cloud providers. But the dual stack support is coming along, and I suspect that that will get a lot more traction once it's available. Will service meshes be integrated into Kubernetes networking SIG in the future? So I'm on record saying I think Kubernetes is already a service mesh, is becoming a service mesh, is taking on more service mesh-like properties. If you look at the gateway work, which I'll let Bowei speak to, you start to see a lot more affordances for things like service meshes. I don't think we're going to absorb Istio or Linkerd or any of the service meshes. I do think Kubernetes APIs will start to cover more service mesh-like functionality. Bowei?
Yeah, I think that's right. It's hard to say if a service mesh is an API or an implementation. I'd say as an API, Gateway may grow up to cover some of the same API space, which is great because if it's portable and it's part of Kubernetes, it's going to be more universally accessible. Specific service mesh implementations on the implementation side, right, then hopefully the service meshes will be able to support these APIs along with their own. And then the idea is that Gateway is extensible, so you might be able to get away with using the portable API rather than having to have a custom one.
Next question, have you considered eBPF instead of IP tables for the default? We've thought about it. eBPF is more complicated, and honestly, my personal preference is to decouple more. Kube-proxy as a monolith has sort of become a problem from a software management point of view. So I'm actually a fan of the fact that projects like Cilium are decoupled from the core project. I think it forces us to be a little bit more honest about compatibility. So thought about it. I don't think we make eBPF the default in the project. We might end-of-life Kube-proxy eventually and tell people that something like Cilium is a better answer. Right. Is NodeLocal DNS enabled by default from 1.18, or do you need to enable it? Bowei?
It depends on your platform. So I think someone just checked. It looks like it's enabled on some platforms like EKS, I think, but it is not. It does take up some resources. So for very small clusters, it probably doesn't make sense. They won't hit that scale anyways. But the way it's implemented, it is a good, especially with the HA and transparency, is a good, easy drop-in if you hit DNS issues.
Next question. Some network control plane implementations allow IaaS-based enforcement of network flows, like NSXT. How do you feel about that way of doing traffic security versus internal policy systems? I don't know what internal here means. What I care about is consistent APIs. And for example, network policy. If you can implement network policy in terms of some other IaaS system, fantastic. But I would, for most users who are trying to get portability with Kubernetes, I would say relying on IaaS systems like that for security directly is going to break your portability goals. So APIs, APIs, APIs. What happens if a cached VIP is no longer valid if the associated pod has crashed? I assume that's in context of the NodeLocal DNS. We set the TTLs pretty low, so caches will turn over reasonably quickly, generally on the order of tens of seconds, I think.
Right. Yeah, and generally DNS does have that caching issue. So that's probably why Kube-proxy exists in the first place.
It is exactly why Kube-proxy exists. What will be the most recommended way to load balance gRPC services in Kubernetes? Oh, you want to talk about this one?
It's an L7 protocol, and it's something that we expect to be the sort of thing we expect to be covered by Gateway. So I know that it load balances on host name, as I understand it. Load balances on host name and path, sort of like HTTP. And that's sort of where the future will go. Right now, you can use some Ingress implementations, I think may support it, but it will be an extension.
And there's some work now happening for proxyless gRPC where you can use a more mesh-like control signal to run your gRPC services without proxies. Next question. How will services V+1 interact with cloud LBs or customer LBs like Metal LB? Will there be improvements to them if they integrate with the new API? Bowei, that's you.
Yeah, at least for the cloud LBs, we definitely, it's in the target of what will be supporting the APIs. I'm less familiar with Metal LB and how it fits in the picture, mostly because it will be relevant from the L4. I just don't know what the Metal LB L7 story is. So it would be great if you ping me on Slack and we can follow up there. I'm just less familiar with Metal LB.
Services across clusters. Can it be via WAN? Is there any latency limitation? There's no intrinsic limitation. Right now, Kubernetes does not really respect topology. So if you have two clusters in two different cloud regions, for example, or if you have them linked across a WAN, it will happily spread traffic across that link, which is probably not what you really wanted. So right now, the implementations that we're looking at are assuming same latency zone. Kubernetes itself will be growing better regionality awareness, and so the vast majority of your traffic should stay local to your own zone, in which case linking up via WAN is a completely appropriate thing to do. Some projects have a custom ingress service like Knative. Will they be able to leverage services V+1?
Yeah, actually, we are working with Knative to make sure that they're compatible. So we had some people in the working group on Gateway basically talk to the Knative folks, and then we had some back and forth. So that's definitely something we're looking at.
Next question. Do you know how the network plugins Calico, Cilium stand with dual stack? Calico, I believe, already supports dual stack. It just can't expose it through Kubernetes because we lack the API. But you can create pods with two IP addresses. Cilium, I don't know for sure, but I'd be surprised if it doesn't have some form of that also. And I imagine most of the others will be relatively straightforward to integrate. Favorite question. What's the time frame for the new service API? When can I have it?
Actually, we have a goal of V1 Alpha 1, and if you attend the meetings or take a look at the notes, we're basically burning down the features. The idea is to sort of get something out in the user's hands to get feedback. I think that's the most valuable at this point. Some things you'll like, some things you'll hate, and we would love to hear all of that feedback.
How will observability be addressed in Service V+1?
Yeah, I had an answer to that. Historically, observability has been orthogonal. So ping me on Slack because I kind of want to understand which part of observability you're talking about. There's some aspects where we are adding sort of extra hooks to put to describe observability, such as request mirroring. But the other aspect, which is like what metrics would be published, that's a separate thing that I think we haven't looked deeply into, but it'd be interesting to sort of get some ideas there.
So if I already have an Ingress controller in place, will I be able to replace it with services V+1?
Well, we certainly hope so. And we're working with all the controller authors. So we did a bunch of reach out to the major controller authors to get them to participate in the proposal. And the hope is that, yes, eventually you will be able to use the API.
Will Gateway support MTLS, rate limits, allow listing, etc.? More L7 features?
Yeah, that is the idea, is we are both making it more extensible, and also some of what is now table stakes in terms of L7 stuff will hopefully be able to be incorporated as a core part of the API.
With the current Ingress resource, I would register the Ingress controller's load balancer IP with a wildcard domain. How would that translate to future gateway class?
There's two. One of them is that if you are, I think I might have misread the question when I answered this. If you're using a feature like a wildcard domain, it should be the gateway. The new API should be a superset. So those features should continue to be like you could be able to express them. The other question is how will it interact potentially with something like external DNS or actually search management as well. And that is an area that we're explicitly looking at, is that gateway and the service APIs not just as a way to express things, but as also a layer that people build on top. I know that for Ingress API, for example, Cert Manager will look at your Ingress resource and then do cert management stuff. And that's the kind of use case that we are also thinking of as part of its design.
So if Gateway will support MTLS, etc., will it compete with or replace service meshes? So this is the service mesh topic. Again, APIs and implementations should be thought of differently. So if Kubernetes absorbs these sort of richer APIs, that doesn't mean we ship an implementation. So if you want to implement your rate limiting API with Istio or with some other service mesh, that's fine, right? It's a plug-inable system. You want to add to that, Bowei?
Yeah, I'd have to just reiterate that, right? There's the implementation, there's the APIs. And it seems like many of the service mesh concepts, it's great. So then they're sort of being absorbed into sort of the base layer. That's a natural progression of the system. In terms of implementation, then, it will be like your favorite thing will remain relevant.
Can you give some more pointers on NodeTrack with regard to NodeLocal DNS?
Yes, although this probably will be worth just discussing one-on-one, so please ping me on Slack. I don't know which aspect of NodeTrack you might be curious about.
So the short answer is you can tell the kernel at the beginning of a packet's lifetime, don't track this packet any further, and it won't go through the rest of the connection tracking subsystem, which means it isn't subject to the normal Kubernetes load balancing, the service load balancing, which means you don't create contract records for it, which is fine if you know that the backend is always a stable IP address like the same host.
Yeah, it's like a 2-for-1. It gives us the HA properties, and also it skips contract.
And contract for DNS is one of the prime culprits that we've seen for people who are having contract troubles. Because DNS is UDP, so there's no connection to close, so you just have to time out those connections. And because they tend to be one request, one response, and then the client opens a new socket. We have just 1 minute left, so we're almost at the end of our questions. What is the status of NF tables as a backend for Kube-proxy? There's an NF tables Kube-proxy project that is happening out of the core tree. I said earlier I don't like the monolithic Kube-proxy from a software engineering point of view at this point, so they're doing it out of tree. If your system is using IP tables on top of NF tables, then Kube-proxy will just use that. Do we have more documentation?
I think there's actually 2 implementations. I think so. It's an interesting space to watch.
Do we have more documentation on Gateway, Bowei?
I just sent a link. It's Kubernetes SIGs service APIs, and as part of the V1 Alpha 1, we will be sprucing up the docs. I think we were trying to get everything in, so the docs might be a little stale, but they should be updated in the coming weeks. Oops, let me make this.
And the very last question that came in was Kubernetes native support for multiple network interfaces. It's still something we're looking at. It's not high on the agenda right this very minute, but it is something I see as eventually inevitable. Keep the conversation going. Visit #2 KubeCon maintainer on our Slack workspace. Please be sure to rate the session. 5 stars.
Thanks, everyone.
We're going to move to Slack. Thanks. We'll see you all there.